So um, here's what we're gonna do. Okay. So we last time we talked about the little bit about chemistry. We talked about the matter, what it is, and we tried to put those matter in the three different phases of matter. Okay. And then we tried to find out the chemical change or physical change. Okay. So once again, the matter is anything that has a mass. So it's any entity with mass and also it occupying a space. Okay? Actually, I want to point out something here. It's any physical entity that has a mass occupying a certain space. This is a mass, but this is not same as the weight. Okay. So weight is technically speaking force, meaning we're standing on the earth. So most of the time we kind of do use weight for measure the mass, the force from the gravity. So this is actually gravitational force. So you can express certain numbers in weight units here. So those are actually in unit of Newton here. This is the one we actually mean by mass, like in real time, like kilograms or pounds, and other units of mass is actually what we do use in science. So technically speaking, like sometimes you ask your friends or the people like how much do you weigh or what's your body weight, everything. Technically speaking, it's actually wrong expression because you're supposed to be saying what is your body mass. Because if you're asking for the weight, they need to say, oh, my weight is 800 Newton. Because nobody answered this one. So anyway, whenever you're gonna do any chemical reactions in chemistry, we're gonna use those mass or sometimes the weight for some quantifiable measurements. So anyway, this was what we covered last time. So we have three phases: gas, liquid, okay, and the solid. Okay. So obviously, the one in the solid phase is really hard because they are strongly bound to each other. So they don't have much of freedom in motion, thus they don't move much. The liquid one, they actually have somewhat freedom, so they can actually move around the space quite nicely and freely in a space. And the gas is the one that has the highest in kinetic energy. Kinetic energy is just the energy of a motion, because this is kind of an energy that certain matter can use to move around the space. So we're going to actually cover about this energy again, but those are the three different phases of matter. So you see the clear difference between ones in each different phases. So obviously the solid one is really highly organized. So if you look at the crystal form, it has very nice uniform arrangement of the atom or molecules in the solid phase. Not much in the liquid and the gas phase either, but only in the solid phase. This is quite unique in this solid phase of the matter. But the gas one is also kind of unique sometimes. This is something we're going to cover at the end of semester, because gas is the only one is actually compressible. So if you think about the solid and liquid, if you try to compress the solid or the liquid one, it's really, really hard. You have to have a lot of force to make it happen. But gas is, relatively speaking, so easy to compress. It's just because for the same reason, you'll see like a big space among the molecules and atoms, because it takes really huge volume of the matter, because they are very high in kinetic energy, so they can move a lot of space among quite a distance among the other molecules too. So interaction between those molecules and atoms are quite, relatively speaking to those two, very weak. So this is why overly can overwhelmed by external force, which is the compressibility of the gas. Makes sense, right? So this is why we are quite easy to compress the one in gas phase, but not those ones. They are, relatively speaking, very high in bonds and interactions is really can be easily overcome those internal force in the metals and liquid and solid. Okay? But we'll definitely cover this one later this semester. This is kind of a the introduction of the three phases over here. So we also went over the chemical change and physical change. So basically, what you really need to know is the chemical change is the one that literally change the identity of your reactants. So it means if you have a certain chemical reactions or chemical change, once you have A becoming totally different compounds of molecule or atom, or the molecules actually. Meaning, for example, if you have a hydrogen oxygen gas molecule making water. Okay. Well, so once you had a hydrogen and oxygen in your hand, now after chemical change you have a water. So water is obviously quite different from the hydrogen and oxygen, both of them. So this is a good example of a chemical change, but the physical change is pretty much the same. I'm not saying, but they're not going to change the identity of the reactants here. So if you have a water in liquid phase, you can put a lot of heat energy into the water, and you'll see the vapor would come out from there. So it does not change the chemical identity of the reactants during the physical change, but it only changes the state of the matter. So it's once in the liquid phase, but coming into the gas phase. So that's very simple, but there was one exception I gave you last time. I'm going to make it quite quick because it's just a review. Was this one. So you have sodium chloride here. We have a sodium chloride, NaCl. This is the salt we consume every day. Okay. So whenever you put this in the water, obviously, as we all know, they will dissolve in water. So meaning when they dissolve in water, they're going to break apart as two different ions. So this is the sodium ion, and this is the chlorine ion. The sodium will carry the positive charge. The chlorine will carry the negative charge. We're going to cover in detail why each one will carry the plus and the other one will carry the negative charge. But if I just tell you briefly today, it's just when you look at the periodic table, which will be given on your exam and quiz, obviously. If you look at all the elements on the left side of the periodic table, except the hydrogen, those are the ones you're going to find lots of metal. So if you have a left side of your periodic table, the most of them, except the hydrogen, is metal over there. And those are the ones will lose electron. So that's why they're going to become positive. And then the one on the right side. So you can have a chlorine on the a third row and the second second right column. That is the chlorine over there. Those are the ones are actually mostly non-metal. There are some in between. We call them metalloid, but we're gonna cover this soon. Those are the ones actually going to be negative, because meaning they're going to gain more electrons. But we'll cover this one later. So don't worry about it. Just if you have a certain elements to look at on the periodic table, this is something you can use. If it's on the left, probably metal except hydrogen. If it's on the right, most likely it's going to be non-metal. Okay, makes sense, right? So okay. So anyway, so if this is the case, this is kind of something we always experience in the nature, in your reality. That something that has positive charge, and the other thing has a negative charge. So they actually carry the opposite charge, right? Then they're going to do what? Do the interaction, right? So they're going to pull them each other to attractive force will be there. So this is why initially you had a compound is made of the positive charge ion, anion, and this is a cation. This is an anion. So cation means this is ion that with the positive charge. So we call this cation. Anion is this is ion with the negative charge. We call this anion. So ionized ion means that is the one that has certain formal charge, certain charge. So they're only going to get this by either losing an electron or gaining electrons. So that means sodium will actually lose the electron. Chlorine is the one that actually gain an extra electron over there. So that's why they become either cation and anion, so they can break apart in water. But before then, we're going to have interaction between cation and anion. So we call this NaCl, ionic compound. Okay, so we call this ionic because they are strongly held to each other by ion-ion interaction. So it's ionic interaction, right? So this is what we call this ionic compounds. And if you guys remember, compound means compound is also a type of molecule, but if that molecule has more than one chemical element, right? So here's one sodium, but there's another different chemical element, it's chlorine. So if these two make ionic bonds, that's ionic molecule, but also ionic compound. Because the sodium wouldn't be a compound, but it's sodium chlorine, because two different elements making ionic bonds. So we call this ionic compounds. You can also call this ionic molecule, but it's kind of weird because the ionic is always going to be what? Compounds. It's a plus and minus can be the same. Makes sense, right? Okay, so there was an exception actually, meaning even though you have a certain ionic compounds going into the water, breaking apart as cation and anion, this is still going to be physical change. So this is a kind of a exception that I just told you on general rule of the chemistry. So this is kind of a one thing you need to keep in your mind this semester, or if you take any other, are you guys taking any other chemistry after this one? If you're taking any chemistry course, here's one thing you can always to remember. We are always going to cover the general rule first. So most of the time, if you use just one or two simple rule, you can just solve the problem right away. But always there are going to be some exceptions. Because in chemistry, of course, we're dealing with a lot of different types of elements. Most of them will follow the general simple rule, but some will just don't do the what it's supposed to be in general rule. So this is one of them too. We'll have a lot more later on. But whenever we have those exceptional case, I'll definitely let you know. Okay, so you can memorize those things separately from the general rule, so you can have no problem with solving any problems on the exam or quiz. Okay, it makes sense. Do you have any questions so far? We good? Yeah, go ahead.
Yeah, why does this make an exception? And what makes this make an exception from the rest?
Oh yeah, this one. So this is a physical change, even though so ions or compounds different thing, but still this is a physical change. So that's a very good question. So if you look at the ions in water, what most of the chemists or scientists think is they're still kind of interacting quite well with each other. Even though they're surrounded by water, that's why they separated. But still, they think they are quite tightly interacting well. So that's why they think if you just vaporize the water, they become a sodium chloride again. So those are the ones kind of a exceptional case. Yeah. But I don't know if you're in a Friday section or if you watch the video, I'm actually think this is a chemical change still. But on the exam, you need to say it's a physical change because more scientists believe in this way. Go ahead, yes.
So if it was like sodium fluoride, would the exception not happen with that? It only happens with sodium chloride?
No, that would be also the physical change too.
Okay.
Yes. Because as long as even though they're ionization in the water, the separation of the water molecule, that's actually a very tricky question because like I said, personally I think it's the chemical change. But as long as the scientists agree upon that those ions still making a quite strong interactions, I can say, it's not a bond anymore, then it's a physical change. So as long as they still have a bit of a same property of the initial compound in the form of an ion. You can see this. That's tricky, isn't it? So that's something. So this is something I'll definitely let you know if there's an exceptional case after we hitting the general rules. But this all needs obvious. I'm not gonna put this on the issue because it's very tricky, right? And also I think it's chemical change too. So. But the only real thing is there are more people believe in certain theory, then there's more prevail of the others. That's what happens in chemistry. So because there are certain boundaries of the making two separate theory, sometimes very arbitrary. So we have certain times have arguments over the certain topic, but on the exam is physical change. That's for sure. Okay. All right. So if that is the case, I'll move on because that was kind of tricky one. So I'm going to talk about once more. But whenever we have a certain chemical change or physical change, the good thing about this one is we can possibly have if it's not chemically bond, you can have a mixture. So mixture means they're not chemically bond, but they just mixed each other. So they still have a little bit of interactions there, but it's not strong as we can call this a typical chemical bond. So for example, if you have lots of sand, which is normally made of the minerals or the carbons and everything, but those particles coming into the water, so you can make some like a sandy or muddy water after mix. But after time, they're going to eventually what? By gravitational force, will sink down at the bottom of the container, right? So whenever you have this type of a mixture, you can definitely tell, oh, this is not, evenly mixed in any portion of the water. So we can call this heterogeneous mixture, meaning this cannot be evenly dissolved or mixed in every portion of the mixture. So when you mix the sand particles and the water, whenever you have sandy mixed water, if you look at the top or the bottom part of the mixture, you're going to have a different amount of the sand or mixed with water because it's not well evenly distributed over the water contents. Okay, so this is why we're gonna call this the heterogeneous mixture. But I could discuss before, if you put sugar, either glucose, glucose or sugar, anything, or the salt like NaCl, if they goes into the water, unless your water is fully saturated with that salt or the sugar, you're going to have same amount of the salt or the sugar are mixed in a certain portion of the water. Meaning, if you look at the water on the top or bottom, you're always going to see the same amount of the salt or sugar there. So, whenever do you like tea or coffee, right? If you put the sugar in a tea to make it sweeter, if you have a first sip, somewhat sweet, right? Whenever you have the last sip of the tea, it's still same sweetness because this is a homogeneous mixture. Makes sense, right? Because if you have a certain salty soup or if you have a certain sweet tea, it's always going to keep the same amount of sweetness that you taste over all portion of the mixture, because those all salt and sugar will be evenly distributed among the water molecules, and we call this homogeneous mixture. Makes sense, right? You get? But if it's not, it's the heterogeneous mixture. If it's well evenly distributed, we're gonna call this homogeneous mixture. Okay, this is the difference between these two types of mixture. So obviously, sugar and water, salt and water, or sand and water, not chemically bond, but they just mixed well. And there are certain reactions, interactions, but not as strong as a typical chemical bond we normally recall. Okay, make sense? So far, okay, good. So let me give you. Let me give you one tricky question. Do you guys like milk? I love milk. You love milk? Do you think it's a homogeneous or heterogeneous mixture? Do you think if you taste the milk for your first day, and whenever you're almost consuming most of the milk, you tasting the bottom part of the milk, do they taste differently? What do you think? It's a tricky one, by the way.
It depends on the milk.
Depends on the milk. That's a good question. How about regular milk? We try. But if it's a, do you think it's a homogeneous?
Starts off
Yeah,
milk,
it
but then
starts
it
off
gets,
heavy.
it'll go bad and it'll gel up.
Oh,
so-
that's really good.
And then it's homogenized.
That's very good. Okay, that's okay. We are excluding the possibility of the bacterial infection over there.
Oh, so
How about
that
that? So here's the thing. The reason why I'm giving you this example is milk is very slightly heterogeneous, meaning it is very close to the homogeneous, but it's very slightly heterogeneous. So I'm just giving you this example because sometimes it's really hard to tell which one is which. So milk is the one good example. So most of the part, the milk is very well evenly distributed, all like the nutrients and all the fats and the proteins and everything. But in the bottom part, you're going to have a little bit of more higher contents of the fat, just slightly higher. So whenever you taste the milk, it almost tastes same. It's really you can really tell the difference much at the first and the last sip of the milk, but it can be still very slightly heterogeneous. So in this case, we really can't tell in detail information. So you can say, oh, this is very close to the homogeneous mixture, but it's very slightly heterogeneous mixture. That's okay to say, if it's not very clear enough to make a one or two. Okay, makes sense, right? So obviously, once again, this won't be on the exam, so don't worry about this one. But I'm just letting you know there are still some exceptional case over almost everything in chemistry. So let's move on. So in chemistry, we just went over what's the matter, what's the three phases of matter, and what might be happening is physical or chemical change, and what's the mixture, or how you can define it and everything. And then also one of the important things you need to do in chemistry is you need to do the certain measurements. You need to analyze the sample, you need to quantify your sample, you need to find out what might be the good information about the sample so you can use it for something else. So whenever you do this, you have mainly two types of the analysis you can do. The first one is the quantitative analysis. And the second one is what we call qualitative analysis. So the quantitative analysis simply means you can actually make exact measurements by number. So it's you can actually tell some quantity there for sure. So if you look at this quantitative the characteristic of the matter, it changes by quantity. So for example, whenever you have 1 liter of water, okay, but you add another liter of water to your sample, what happened to your mass of the water? Will increase or decrease?
Increase.
Will increase, right? So if you're adding more of that compound or more of that matter, if they changed your mass measurements, that's what we call a quantitative characteristic of the matter, because it changed by its quantity. So whenever you add more, or you can subtract something part of the matter, if that changes that the character, we can call that it's a quantitative analysis measurement. You can also say, so mass is one of the good example, and volume as well, because it can be changed by controlling the quantity of the sample. Makes sense, right? Perfect. Okay. So how about the qualitative one? So you have a qualitative one, it's pretty much the same but opposite way. So whenever you change the quantity of the matter, it's still not changed. So for example, if you try to analyze the color of the water, no matter how many liters or grams of the water, the color of the water will be still same, right? Or you can say texture is a pretty good one. Texture will be almost same, even though you had a lot or less, doesn't matter. You can have a boiling point or melting point, or there's so many things that you can still try to analyze and measure, but it doesn't change by controlling its quantity, and it's what we can call qualitative. Okay? Because it only depends on its quality, not by quantity. Makes sense, right? Okay, perfect. Alrighty. So, if that is the case, for quantitative analysis, what we normally have to do is the unit conversion, because we have so many different units for certain physical property of the matter, mass or volume, or some of the temperature unit as well. So we actually call this one dimensional analysis. So dimensional analysis simply means if that matter has a certain type of physical property, you can actually switch that measurement onto the different units by using similar physical property. So meaning, for example, you have 1 meter is equal to 100 centimeter. So you have two different units here, which one is meter, the other one is centimeter, right? But their both can be used for what? Measure the length. Perfect. So meaning those two units has same physical property, right? Measurements. So meaning you can change any number meter to numbers in centimeter, no problem. So this is why we call unit conversion as one of a dimensional analysis. It's pretty much the same thing. So we're gonna do this one also with the sorry, the mass. So this is the length. Okay, we can also do the mass because we get to this one to the volume. Okay, so mass, once again, mass and volume is a very good example of quantitative analysis, right? So we need to know how to do the unit conversion for those two, so you can have a lot of good dimensional analysis on certain matter. So the mass-wise, for example, you can have 1 kilograms is equal to 100 grams as well. So same here, 1 kilogram, 1,000 grams. It's just those units are also only for mass. Okay, mass. Okay, so you can actually also do the unit conversion from here to here, here to there. It's no problem. Okay, so one of the things we normally do in chemistry is the unit conversion for density. So density is this one. So you have a certain mass over volume. So that will actually tell you the unit mass of something. That is the density. So how heavy your sample will be in a certain unit volume. That's the density. Makes sense, right? Okay. So density is simply same as mass over volume. So whenever you express the certain number for the density, you're gonna use the unit for the length and mass. And now you're saying, what do you mean? Because you only have a unit for the length. But how do you express number in volume? It's simply using this way. So we all know we live in the 3D, two-dimensional space. We do live in, well, some talks about the time, but anyway. So whenever you do have a three-dimensional space, each measurement of each axis over y and x and y and z can be expressed in any unit in length, right? So if you want to express something volume, only thing you have to do is multiply as the, I'm going to write larger, width, height, and the length. Okay? So simply just make a cubic like a space. So you have to have a certain width and height and length. It will make some good 3D space. That makes what? Volume. Makes sense, right? Good. Perfect. So if that is the case, only thing you have to know for getting number for the density, you just need to get the length, and then you're gonna put it in the cubic space, so you can make it volume. So for example, you can do centimeter cube, meter cube, and so forth. So the numbers for the volume will be always in certain length unit cube. So that's a volume, unit for the volume. Right? Okay. Good. So we're almost done. So once again, density is mass over volume. So for example, if you have a 1 gram per centimeter cube, okay? Meaning, if you have the certain unit here, that is 1 centimeter, and 1 centimeter here. I'm gonna draw it bigger. So, if you have this space, each side is 1 centimeter. Okay. That will make this 1 centimeter cube space, 3D space. And if you have this much of the sample, that sample will weigh about 1 gram. That's what it means. Then that's density. So this is one good example of density. 1 gram per centimeter cube means you have a 1 centimeter cube, much of the sample will weigh about 1 gram. And that's what we mean by density. How heavy that will be in a unit volume as we define in units. Good? Perfect. All right. So now we get to the how we get to the number for the density, and let's do the unit conversion here. Okay. So I'll probably do this again on Wednesday because it's quite an important part of the chapter 1, and also almost for anything you do in chemistry, especially in the lab. So let's do 1 gram per centimeter cube. Okay. But I want to change this in the different density unit. So I want to change this one to kilogram per meter cube. Okay, this is my job. I want to do. Okay, and let's see how we're gonna do this in here. Okay, so whenever you have this number here, what I'm gonna do is I'm gonna make a table. So once again, you have a slash over there, meaning it's in the top. This is the bottom. Okay, this is the numerator unit. This is the denominator unit over here. So this is the same as 1 gram over centimeter cube in the table. Okay, if you make a table over here, this is 1 gram over centimeter cube. Okay, so normally when you do the unit conversion for the density, it's better if you do the unit conversion for the mass first because it's easier. So only thing you have to know is the unit conversion factor. So like I said before, 1,000 gram is equal to 1 kilogram, okay? So if that is the true, this is the unit you want to convert into the kilogram. So now this is on top, on the table. This is at the bottom. So to make this unit cancel, you have to put this same unit, which is gram, at the bottom. So whenever you get the conversion factor, which is this one, you're gonna copy this 1,000 gram at the bottom. So you can cancel the same unit top and bottom. If you have the same unit and top and bottom, you can cancel them. So you have a 1 gram on the top, but you're gonna copy the 1,000 gram at the bottom, so you can cancel the same unit over here. Okay, so you can cancel the same unit. And you're gonna copy the new unit that you wanna switch to on the top. So now you cancel the what? Gram units, but you put them on kilogram right now. Okay, by just dividing 1 by 1,000 right there. Okay, and then this is a bit tricky part. Let me actually move to this way. So 1 gram over centimeter cube. So you change this one to this way. And then this is a bit tricky. So for this one, 100 centimeter is equal to 1 meter. Okay, 1 meter. So I'm gonna put this one same thing, but this is the bottom. So at this time, I'm gonna put this one on the top so they can be canceled too. So I'm gonna copy the 100 centimeter on the top. I'm gonna copy the 1 meter at the bottom, okay, in the table. But here's the thing, whenever you do this, what you really need to do again is this is a unit conversion for length. This is not the volume yet, but the unit that you have originally in the 1 gram per centimeter cube is centimeter cubed. But this is still in what? Length units. So to make those two in volume, you have to cube everything, top and bottom. Not just the unit, but also the numbers. So you're not just cubing the units, you also need to cube the numbers too. So this is not 100 centimeter cube. This will become 1 million centimeter cubed. Because you have to cube the 100 too. So 100, 100, 100 with 1 million. Okay? But this is easier because the 1 cube is just 1 still, and meter cube over there. Okay? Makes sense, right? So if you do this, only thing what you need to do when you make this table, finally you have grams are canceled here, same, and now those centimeter cube are canceled too. So you now indeed have top and the kilogram at the bottom meter cube. Okay, but now you have to do the calculation. So only thing what you need to do is 1. You started with a 1, but you have a 1,000 at the bottom, meaning you have to divide this 1 by 1,000 because you have 1,000 at the bottom, right? And you also have a 1 million on the top and 1 at the bottom too. So you don't have to worry about the 1 because 1 divided by 1 is just that number, right? But you have a 1 million on the top, so you have to divide this number by 1,000 and also multiply this by 1 million. Okay? If that is the case, right, you can do this one. So it's 1,000 kilogram per meter cube. So this is the same density but in different unit with 1 gram per centimeter cube. So they meaning the same density but just different units. That's why they're in a different number. Makes sense, right? Kind of? Okay. So the let's try to do the other way, okay? And then I'll finish now. But I promise you, I'll do this again on Wednesday, okay? So you can either watch on the YouTube while you're in the Wednesday, you can come in class for sure. And also, if in Friday, you can, start to look for certain open chair, but if it's not, still again. So let's do this in the other way. How about we have a 500 kilogram per meter cube. So we're now doing backward, okay? I want to put it in the gram per centimeter cube, okay? So if this is the case, we're pretty much gonna do the same job, but in the opposite way, right? So this is a 500, you start with 500 and try to make a table, okay? And then once again, kilogram is the numerator unit now, so you're gonna put kilograms on the top. I'm gonna put this slash down, it's a meter cube at the bottom, okay? So once again, to switch this kilogram to the gram, you need to use 1,000 gram is equal to 1 kilogram. So if that is the case, now you have to cancel the one on the top. So I'm gonna copy this one at the bottom. So now I'm gonna actually put this 1 kilogram at this time at the bottom, not on the top, because you have this one on the top. So they can be canceled right over here and over here. So that means you're actually going to put 1,000 gram on the top. So you can have a new unit for mass, which is gram right over here. So you now see the kilograms are canceled top and bottom, and now you have a new unit on the top with the gram, and you have to have also 1,000 number over there too. So now we're done with the mass. Okay, let's try to do unit conversion for the volume now. Once again, so you have a unit for volume at the bottom, meaning you have to put those unit conversion factor, but once again, this is still in the length unit. So we're gonna put this one on the top, and also cube. Okay, we have a 100 centimeter at the bottom. That's a cube. Okay, so in this case, what you're going to do is you're going to have 1 cube is still 1. Okay, so this is 1, and but meter unit also will be cube, so it's 1 meters cubed. Okay, if you cube 100, that will become once again million. Okay, and also centimeter is also cube, so it's centimeter cube. Okay. So in this case, now we have these units are cancelled too, and finally we do have a new numbers in gram per centimeter cube. So only thing you really have to do is what? This is a 500 we started with, and you have a 1,000 on the top, 1 million at the bottom here. Okay, so meaning you have to multiply 500 by 1,000, and then divide those multiplication by million. So meaning you have a 500 times 1,000 over 1 million. And then now you have that number in gram per centimeter, which is 0.5. So 5 over 10 is 0.5. Okay, so you have 0.5 gram per centimeter cube. Makes sense, right? Okay, so I'll stop here.